In this video, we're going to perform a nonlinear analysis on our data. And this data came from a physics experiment measuring the magnetic field of a magnet at different distances away from a sensor. And the sensor in this case is a magnetometer sensor inside our smartphone. Initially, we had to perform a statistical averaging of all the repeat data. So if you're interested in that, look at the previous video. In this video, we're going to look at how we can perform a nonlinear analysis of this data, because the data follows a physical model for a magnetic field, which is B, which depends on a couple of constants here. And this parameter of interest is the magnetic moment. And we expect this function to depend on the distance. The distance here we call r, and it should depend on r to some power n. So the 1 over r to the power of n, some kind of inverse power law, and our analysis of our data should tell us how the magnetic field varies as we move away from the magnet. So I'm going to perform this analysis using Python, and I'm going to run the Python code and write it in a platform, an online platform called CoCalc. So here we are in CoCalc. CoCalc is this free website that you can use to program in. And here I'm showing you the results from our previous video. The previous video was all about how do we combine all the thousands of repeat data points to get an average. And the average here is the average magnetic field as a function of distance, or. So all of those repeats have been combined. So for each distance, we've got the average field and we've got the error on the mean. So the error value there. Next, I want to analyze this data to determine how strong the magnetic field was at the source. What is the magnetic moment? And also, what is the inverse square relationship? And to analyze the data, I'm going to create a new file. And like before, I'm going to program in a Jupyter notebook because it's very visual and it suits this purpose very well. So we'll call this file analysis, and we click on Jupyter Notebook, and that will give us a Jupyter Notebook file. So that will open. Now I'm going to construct this program kind of organically. The first thing I want to try is to import the data again. So to import the data and to do the analysis itself, we're going to use a key Python module called numpy. So I'm going to import numerical Python, or numpy. And I'm going to give it a short name, np, as before. I would also like to visualize the data and the results. So I'm going to import matplotlib. I'll shorten the name to plt. And the first thing is to import the data using numpy's load text. The data file, we've called it mean data. And as we can see, there's no delimiter, it's a space or a tab. We've a hash symbol on the first line, so the interpreter will ignore this first line, which is good. And let's see if this works. Great. So again, I'm going to make a little diagnostic cell here so I can test out what's happening at each point in the program. And the data looks good. I've got 3 columns, and the next thing I want to do is separate the data out. I can do this one of 2 ways. I can import it all into a variable called data, or I could effectively separate the different columns out using what's called the option in load text called unpack. And unpack will set equal to true. Now unpack will unpack each column into a separate variable. And the variables are these 3 here that I'll use. So the first column will be unpacked to a variable called or. The second one, we'll call it b field. And the final one, we'll call it error. So that's the error on the mean. So let's see, will this work? Great. And just to check, we'll use this command whos again, like in the previous video, to check what we're loading into memory. And as we can see, we've got our B field, 27 values for the error and 27 values for the distance or. Okay, great. If we want, we could do a quick visualization of what the raw data looks like. So we could do a plt.errorbar, and this is just an error bar plot of the distance and the B field And finally, we want to put in the error. So we can say error, and we will format the points to look like circles. Otherwise, defaultly, the plot will have joined up the data points, which makes it a bit tricky to see what the data points are. So we'll set the data points either to a circle or to some kind of point. And let's see, will this work? Great. We've got a clear drop off with distance, and that's the key characteristic we want to analyze. And the error bars also are tiny. We cannot even see the error bars. We can look at the raw data and we can see that the error bar is 10 to the minus 2. This is 10 to the plus 3 on the main value. So there's a factor of 100,000 almost between the error and the value. So that is a really good thing. It means the statistical error that we got from averaging all the repeats is really low due to the high number of repeat readings we got. Okay, so that's nice. So we have our data loaded in, we visualized it, and next we want to begin the analysis. Now before the analysis begins, I want to scale my data to get it in the correct units. So let's get rid of the plot for now. And the distance variable I want to scale to meters. It's currently in centimeters. So I can say my distance is equal to the distance itself multiplied by 1 by 10 to the power of minus 2. So that will go from centimeters to meters. It's also clear from when we took this data and we recorded these notes in a little readme file that we have to correct the distance values that are written on the file names by adding a value of 0.5 centimeters. So half a centimeter needs to be added on to each distance. This is because the file names that we saved it to is only to the nearest centimeter. So we want to make sure we've got the right distances. So let's correct that. So we're going to convert the distance to meters and then add on half a centimeter. Next, we want to convert the field values to Tesla. At the minute, they're in microtesla. So B field is equal to B field. And likewise, for the error on the mean, we're going to convert that to Tesla as well. So we're working in base units, base SI units. So when we do our final calculations and analysis, the units are correct, and we don't need to worry about factors of 100 or a million missing here and there. So that's scaling the units very easily. Once we've got the units scaled, we can start the analysis. And while we're working, we might as well add some comments here. So we're going to load the data, and we're going to scale the units. And next we want to attempt a nonlinear analysis of the data. So let's look again at what the data looks like. So we'll plot the data again. So we can see that our data follows some clear inverse relationship with distance. So as distance gets larger, the value of the magnetic field decreases. As we mentioned earlier, our physical model that we're looking at in this experiment is an inverse law that depends on the distance or. So this is the magnetic field. It depends on these three constants divided by distance to some power n. So we want to determine the power n, so whether it's 1 or 2. We also want to determine the magnetic field moment. This tells us how strong the source of the magnetic field is. So we have these two values we want to determine from our analysis. M, the magnetic moment, and n, the power. So let's crack on. So at the moment we've loaded in our data and we've scaled the variables. To proceed to the analysis, we're going to import our analysis algorithm. And the algorithm is called curvefit. And you'll find it in SciPy, which is Scientific Python, a big module. And it's in the sub-module called optimize. So whenever you're doing regression analysis, where you're comparing data to some model, you're optimizing the fit. So this optimize submodule contains the algorithms for this. And it's curvefit with an underscore between the two words. This will import curvefit that we can use. The syntax for running curvefit is relatively straightforward. We have a few different arguments that we need to put in. The first argument is a function name that we're going to have to make. It's the function that we want to compare our data to. Looking at our model, we can say that b is related to 1 over r to the n. So that's some kind of power function. So I'm going to call my function power law, and I'll define that in a second. The next argument is the independent parameter or, and we've got that already. Then we want to give the curve fit algorithm the data we expect for the B field. We're also going to provide the errors on the mean, and that's assigned to this variable called sigma. And we're also going to provide an initial guess, a starting point, and that's going to be assigned to this variable p0. So that guess is a collection of things that I'll just describe to you in a second. So before we proceed, we have to define this fit function. So the nice thing about curve fit is that no matter what data distribution you have, no matter what shape the data is following, you can define the specific function that you want to check against, that you want to try to fit with. And in this case, we're going to use a very simple customized function. I'm going to call it power fit. So the power law, I'm going to write a little expression up here in maths for you. The power law is in mathematics described as some function, we'll call it f of x, is equal to a multiplied by so a is some constant, and x is your typical independent variable, and x is to the power of some power b. And this is the function we want to define in Python here. So power law needs these arguments. So I'm going to have an argument x, which is the main independent variable, and the two other variables are a and b. So these are the parameters that we want to kind of get out from our curve fit. Now this function is very simple. It just returns the product of these things. So it returns a multiplied by x to the power of b. As always, we can put in a very simple docstring to tell us what the function does. So we'll just put a note here to put a docstring. But the function is very simple. We give it 3 arguments and it returns the value represented by ax to the power of b. And we're going to ask curvefit to use OR for x and to vary the values of a and b itself until what's it returning is close to the b field value. But ultimately the algorithm is taking our values of distance, mapping that to the x variable here, and then it will vary the values of these two parameters a and b until what it's predicting is as close as possible to what we've measured. Now what's nice about curvefit, it uses a chi-squared algorithm, and that style of algorithm includes the error bars in fitting the data to the function. As we've seen here, our error bars are tiny, so they won't have any effect. To help the algorithm along, we should try to give it an initial guess. So the initial guess are the two values for a and b here. The amplitude, we can say, is somewhere up here. Maybe it's 0.0013 or 0.0012. It doesn't really matter how close our guess is. It just needs to be a relatively easy starting point. So it's going to be the value for a, and the value for b, remember, is this power. Now it could be decreasing with an inverse square or inverse cubed. I'm going to go for an inverse square for now, as for the initial guess. We're going to wrap those two values inside an array. So to make a numpy array, just type numpy.array, round brackets for the function, and then inside, to make our array, we use these square brackets. So P0 is a very simple array containing two values that will get used here. I should say not P0, but guess. Guess is the name of the array, and then that's been mapped into this function variable P0 that curvefits use. Now what curvefit outputs is hopefully the optimized values of our guesses. So A and B. Now the optimized, we can give them a name. So we've got maybe optimized parameters, p-opt. It will also output another array, which is the variances, and we'll use those variances to calculate the uncertainty. And the variance, we can call it pcov for covariant matrix. And you'll see this is a standard kind of syntax for running curve fit when you look at other sources. So let's just give ourselves a comment and perform analysis. And let's see if there's any errors, anything wrong with our code. No, all good. And we've got a few more results here. We've got p-opt and we've got pcov. So p-opt is just 2 values, which is good, and pcov is a 2x2 array. Now I'm just curious what p-opt is, so let's have a look. So I'm just going to type p-opt and hopefully it makes sense. Okay, so the easy number to understand is this one here, minus 1.75, roughly minus 2. So this is B here. So the optimized values that are returned out of the curve fit algorithm are the optimized values for these 2 variables, okay? The first variable is A, and A determines where this power curve starts or how it's scaled. Greater values of A push the curve to the right. A is in fact the value of x that gives you a value of 1 for the function. The second value returned by our curve fit algorithm is the value of B. This is the power that we're interested to know. So the power, just to remind ourselves, is this variable B that we had up here when we defined the function. This is the value that we want to know in order to determine what power the distance has. So this n variable in our physical model. So we can see from our results that the optimized value of this power that the curve fit algorithm calculated was around minus 2. So minus 1.75. And this is what we'd expect. We'd expect an inverse power law, so that as you go further away from the magnet, the field that you measure is less and less. And we expect this to reduce with the square of the distance, so the inverse square of the distance, to make an inverse square law. Now, you notice it's not exactly minus 2, so I'll be interested to look at what the error is. So any fitting algorithm has to compare data to get a best fit. It's always an approximation, and it depends on how many data points you have and the quality of your data. So knowing the values of the errors will enable you to put these numbers in perspective. Is it a small error that could change this potentially up to 2 or less than 1.75? And the errors are really important to finalize your analysis. So without the statistical errors on your analysis, you don't really know how accurate these results are. So to get the errors, firstly we have to understand what's stored in this second output, pcov. Pcov has got a bunch of numbers. It's actually a 2x2 array, and these are the variances of the fit values. We won't go into the details here, but to get the error from a variance, you essentially take the square root. So these are the errors squared. So we want to get the square root of the values. And the pcov values we're interested in to get the square root is this value and this value. So to calculate the uncertainties, we can get the square root of those values. So we can say that fit errors is equal to numpy that diagonal. So we're going to get the diagonal of this array, which is called pcov, and that will select these 2 values. And we want to get then the square root of those results in order to get the errors. We can combine these 2 steps in one to get the square root of the diagonal, run that seems to run, and we can then check out what those values are. And then we can check out what those values are for the fit errors. So we have the uncertainties on our fit values. So let's put them side by side so we can look at the difference. So the p-opt values are here. So we have relatively large uncertainties. So we got around 10 here, and we've got around 2 here. So that's 2 out of 10. So it's around 20% uncertainty on the scaling value, this A variable. And on the power, we've got a smaller error. So this is around 2 here, -2, and this is 0.05. So 0.05 out of 2 is the same as 5 out of 200, or 2.5 out of 100, so it's around 2.5%. So the error on the power is quite small, whereas the error on where the curve is scaled from is quite large. And that's not surprising. The scaling value that we have is 8.57, so this would be the x value where you get a function value of 1. So 1 is way up there. So the scale is very small, so 1 is very far away, and since our data doesn't go anywhere near a value of 1, the uncertainty on where that is will be much higher. So this is why we have roughly 20% error on this variable that we fitted. This is the variable we're talking about, this optimized A here. And that A corresponds to these 3 constants in the physical model. They get combined into A, the power n correlates with this B value, and of course distance is this x. So we have an uncertainty on, a larger uncertainty on the combined 3 constants. These 2 constants, u0 and 2 pi, have 0 error effectively, whereas all the uncertainty will be on the magnetic moment, and it'll be useful to calculate that. So once we have got the fit errors, we can separate these values out. So let's get rid of some cells there. And I just want to print these to screen so we've got the real values. So now that we've calculated the fit errors, let's calculate the value of the magnetic moment, and we can also calculate its error as well. So let's make some space, and we'll add a comment here as well. We'll say calculate magnetic moment. So this is the main result of our analysis that we're eager to find out. So firstly, we'll need a value of the mu0 constant. I'm just going to write that here. So it's a well-known number in physics. It's got a precise value, and we can use that now with p-op0. So p-op0 is the optimized value of these 3 constants combined. So I'm going to have to do some multiplication and division to extract what m is. So m is equal to 2 pi multiplied by the fit parameter for those 3 constants, so p-opt0, all divided by mu0. I also want to work out the uncertainty. I'll call that dm. So dm is going to be equal to the value of m multiplied by the relative error on the fit parameter. So the relative error on the fit parameter is the error, which is fit error first value, which is index 0. So the relative error is that divided by p-op0. So that's the relative error on p-op0. So in brackets, we've got the relative error on the fit parameter, and then that relative error will transfer to be the main error on magnetic moment. Now let's print that result to screen. So we're going to print the value of the magnetic moment and the error on that value. And we're going to add units as well. So let's all put that all into a print statement. The units will be amperes meters squared. I'll print that to screen, and it tells me that my magnetic moment, so the strength of my magnet, is 4.3 plus or minus 0.8. So we're going to ignore all of these many digits, because as you know, most of these digits aren't physically valid. If we round our error to one significant figure, we get 0.8. And one significant figure on the error is the standard precision we tend to run our experiments at. So 0.8 here will give me 1 decimal place. That means I've got 1 decimal place here of precision on my main value. So that's 4.3 plus or minus 0.8. Next, I also want to print out the value of the inverse power, and we can also calculate the error on that. Now, there's no scaling for that error, so it's just exactly as the calculation has from the main algorithm. So we can print that to screen as well, and we get minus 1.75 plus or minus 0.05. So there's no units on this, it's just a numerical value. So the error on the power is much smaller compared to the relative error on the magnetic moment. Now, that's our analysis results. These are the important numerical values that we want to get from our data. As a final step, we also like sometimes to visualize the analysis results as a curve, as a line, and compare it to our raw data. So we're going to create some fit data so we can visualize the fit. The raw data that we have down here, we've got Y data and X data for the raw. I also want Y data and X data for the fit. And the fit is this function that we're going to put alongside. You'll see that in a second. So to create the X data, I'm going to go from roughly 0. I'm going to use X values all the way towards the end of my data here. So we're going to use numpy.linspace. It creates a linear array of values, and we can start wherever we want, which is 0, and we can end at 0.3 roughly. I'm also going to ask for 100 values, so that makes our curve look a bit smoother. Default is just 50 values. And the Y fit is the fit function, which will be our analysis results. To get the fit function, we use our fit parameters, and our fit parameters are calculated from the curve fit. So we're going to use the p-op values, and we're going to stick those values back into our power law and use our x fit values for the x variable here. So let's do that. So we've got the name of our function that we've written, power law. We're going to give it the x values that we've just made, and we're going to give it the optimized values for A and B, which is p-opt index 0, and the second one is p-opt index 1. So that will create Y data using a power law function. Next, we want to visualize the raw data, and we're going to put on top of that the analysis data, and we're also going to add some labels to the axis. So here we've got the raw data. Next, we'll plot the fit data, and we're going to plot it using a red line. We're going to give the line width 3, and here are the labels to tell us what the units are. So let's run all of that. This is our final analysis script, more or less. And what we can see here is that our blue data is here, and our red data has gone well beyond our blue data points. So the red is the analysis results, this kind of Y fit and X fit that we made. So I don't want to go that far up, so maybe I'll start, instead of 0, I'll start somewhere close by here. Let's go a bit closer, maybe 1.5 centimeters, which is 0.015 meters. Great. So our red line now is the analysis results, and we've overlaid it pretty close to where our data is, and maybe we will bring back the other data point here. So we'll go towards maybe 0.28 meters. See what that looks like. Great. Okay, I'm happy with that. So the last thing we need to do is save the figure. So we'll do plt.save fig, and we can save it by default as a PDF for high resolution. If a PDF isn't your preferred format, PNG is another format you can use as well. So now we've completed the analysis. We now know the magnetic moment of our magnet is quite strong. So it's around 4 ampere meter squared. And that data follows a rough inverse square law. It's not exactly to the power of -2, but it's relatively close. Now finally, bear in mind that you can adapt this script. This is the final script to provide a template for any nonlinear analysis. All you have to do in future is to identify what mathematical function you want to analyze, and instead of a power, it could be a log or an exponential, and all you got to do is change the mathematics in your fit function. Instead of a power law fit, it could be an exponential or a log, whatever function it is. You load your data the same, and most of the calculations you can adapt quite easily. So this can serve as a template for all your future nonlinear analysis work, and that's it.